Today we are going to discuss about PSC Concrete Sleepers. PSC Concrete Sleepers were first introduced in France around 1940, and after World War II it was developed and also used by British and German Federal Railways. Large-scale experimental investigations and field observation conducted during the period of 49 to 53 with more than 3 million sleepers on track, and they confirmed that the Prestige concrete sleepers are really advantageous. And then they introduced the Prestige concrete sleepers as the new structural member of the permanent wall. And as at the last 2-3 decades, this sleeper demand of concrete sleepers is getting more and more, especially in high speed and heavy traffic density tracks. Each country has adopted particular types of sleepers depending upon the cost of materials, labor, national track requirements, also their availability of their indigenous materials or their technology. The development in sleeper design extending over the last 3 decades has resulted in the adoption of different types of pre-stressed sleepers, and the prominent types are like two block sleepers connected by pipe filled with concrete and containing high tensile bars for compressing the concrete in the blocks. Especially in Sweden, this type of sleepers were used. Then, most common, especially in India, it is the beam type single piece pre-stressed concrete sleepers. Contrast to the two block type or beam type sleepers are flexurally stiff because it is continuous over the entire length. Also have the additional advantage for providing greater measure of rigidity to the track. Also, it prevents rotation at the sittings, buckling of the rolls. So, solid heavy prestige sleepers have thus made possible the adoption of long welded rails, and also that's why it helps in smooth running and also increase the safety of the vehicles as well as the permanent way. Now, to design a sleeper, it is important to know that the principal function of a rail rope tie is to distribute the wheel loads carried by the rails to the ballast. Right. Though sleeper is a simple determinate structure or structural element, it is not possible to precisely evaluate the loads and what will be the loads that may come during its service life, because there are many uncertainties, complexities inherent in the variables, still very inadequate knowledge of the dynamics of the track structure. So there are some factors which influence the design of sleepers. One is the static and dynamic loads that imposed on the rail seats depend upon the type of track. Is it straight or curved? Is construction standard of maintenance, the axle loads, their spacing, the running characteristics, speed and standard of maintenance of vehicles. So static and dynamic loads depend upon these many factors. Another factor which influences the design of sleeper is the ballast reaction, which generally influenced by the shape of the sleeper. Is flexibility and spacing, also unit weight of the rail and the standard of maintenance of the track, the characteristic of the ballast. Now we are talking about only static loads, and loading standards and the associated hypothetical ballast pressure distribution generally evolved by various national railway organizations, and they got their pressure distribution based on their laboratory as well as the field investigation, and whatever they got from their investigation are mainly from static loads, so they just increased the static loads to account for the dynamic effects. And for static and dynamic loads, a static wheel load of 110 kN at the railhead with heaviest locomotive was found to cause a vertical sleeper reaction of 60 kN on a straight track at the rail seat. Okay. A wheel load of 110 kN which are being applied at the railhead, which will cause a vertical sleeper reaction of 60 kN. If it is on the curved tracks, the maximum horizontal wheel load was observed to be 120 kN, which will be acting at the railhead. Right? Now, let's consider the distribution of this load among several sleepers. Right? It was estimated that 60% of the horizontal reaction is to be resisted by each sleeper. Okay. So due to lateral forces in the curved tracks, the magnitude of the vertical force is increased on the outer rails and reduced on the inner rails. Now, to allow for dynamic effects, Indian Railways have adopted a design load of 150 kN at each rail seat based on the static load of 60 kN, which is amplified by a dynamic factor of 150%. To calculate the ballast reaction, a hypothetical distribution is assumed, and generally assumed in such that the bending moments computed on the basis of a assumed pressure distribution, which should more or less conform to the bending moments which actually developed at the critical section, such as the rail seat or center of the sleeper, which you can get. They have done extensive field observation. From that, if you are getting that this much bending moments are happening at the rail seat or center of the sleeper, so based on that your pressure distribution should be like in such a way that your assumed pressure distribution also create the same bending moment at the critical section. In addition, the pressure on the ballast should not exceed the permissible allowable pressure on the formation. Okay. Now, ballast is well packed under the rail seats, while the central portion of the sleeper is kept loose to avoid center binding. But the packing gradually works loose under service over a period of time, and the reaction starts building up towards the center of the sleeper. This reaction start building up at the center, which was first was 0. Now as the time goes on, the reaction start building up at the center also. So how much it can build up? So that is given by a center binding coefficient alpha, which is defined by the ratio of intensity of pressure at the center to that under the rail seat. This ratio is the intensity of pressure at the center to that under the rail seat. But this alpha will depend upon maintenance standards, climatic condition, length of the sleeper. So it's been reported that the moment at the center of the sleeper shoots up by more than 10-fold if the center binding coefficient increases from 0 to 0.5. This coefficient alpha, if it's getting from 0 to 0.5, as time goes on, is getting bigger and bigger, and as this reaction builds up, the moment at the center becomes more and more. So now, how much we can take the moment at the center then? So now field observation done by German railways indicate that for sleepers designed for a bending resistance higher than 10 kN at the center, if you design your sleeper taking moment at the center as 10 kN, the bending resistance, or more than that, then your percentage of failure due to cracking on the concrete is becoming of the order of 1%. So your chance of failure becoming less if you design your sleeper for bending resistance which is higher than 10 kN. And just so thus India also following this. Now for the broad gauge railways, they design the sleeper for a moment capacity more than 10 km so that they can safeguard against, especially in the area with black cotton soil where the chance of becoming the swelling of soil is much more, where the ballast pressure at the middle can become more. So if you take the bending resistance or moment capacity more than 10 km and you are designing for that, then that adverse formation can be avoided. Now the draft Indian Railway Standard specification have laid down some acceptance criteria for sleep. So now for testing of sleepers under dynamic loads, the Indian Railways have tentatively stipulated a load range of 5 to 20 ton and a frequency of 500 cycles per minute for 2 million cycles applied at the railway, and the sleeper being supported on a span of 560 mm below the railway. And when the resulting crack will happen, when you are removing the load, it should not exceed 0.05 mm. After so many cycles of load given, your resulting crack should not exceed 0.05 mm in width. Also, a minimum failure rate load of 37.14 ton has been prescribed for the rail seat bottom section. Now, according to this standard, the cracking load should not be less than 18.5 ton for section at the rail seat bottom and 6 ton for the top of the center of span and 5.25 ton for the bottom of the center of the span. Okay, this is given by the draft Indian Railway Standard. Now the axle loads, train speeds have been gradually increasing over the last few years, and it is likely that the speeds of about 200 km per hour could be a common feature for the rolling stock in the next 20-30 years. So some of the advanced countries are already experimenting to develop new form of permanent way. They are experimenting with continuous concrete slab with longitudinal and transverse pitch tracing without ballast, which are known as ballastless track. Already is being used in some countries already, and especially to cater the needs of high speed and high density traffic 21st century. I think you have gotten a little bit of idea of the some design consideration. What are the advantages and what are the basic design loads that being considered while designing a sleeper. Thank you.